Okay, let's get started. It's Friday. Did you get the textbook yet? Do you have it in your possession? Good, good. It's important to read. It's a good book. It's kind of the standard, the de facto standard in environmental engineering. It's considered there's not a lot of competitors to this textbook. I hope you find it readable. Just as a reminder and a correction, I think last time in class on Wednesday, I incorrectly mentioned that the presentation by the faculty candidate would be at 1 o'clock. And it's not, it's at 2, it's next door after this. So if you're available, I'd be delighted to have you join that presentation. And if you just respond to a brief homework assignment that's optional and posted in Blackboard, you can get 10 bonus homework points. So that's basically one problem. It's no huge incentive, but I mean, if you'd like to be there, I'd be glad to have your participation and see what this faculty candidate, what you think of him. So looking a little bit further to the future, you've just submitted homework 1, hopefully. That introductory assignment was due at the beginning of class. And then homework 2 is due 1 week from today, materials balance and kinetics, which we're going to continue talking about today. And then Monday the 27th, we'll have a very light-duty quiz in class. It'll be your first assessment where it's on the spot. What do you know? It's only worth 1% of your grade, so the stakes aren't too high. But any questions on the announcements before we start talking more about materials balance and introduce some ideas related to kinetics? All right. You guys are going to think that I have no technological capabilities whatsoever because the printer, for whatever reason, it punched out the right side of these papers instead of the left side of these papers. And I've been using that printer for ages, and just for some reason, it punched out the wrong side. So we're going to start with a brief in-class exercise, thought activity about activated carbon. So let me hand out these papers to you. You can get started thinking about this. I'm going to ask you to please get on your phones in class today. Please get on your phone or your computer to do a little bit of research about activated carbon. Like, what is it good for? What kind of chemicals or constituents does carbon filtering work for? So just have a look at the questions on here, and then problem 2 is a little bit more quantitative in nature. Problem 2 is some calculations here, just what we've learned so far about units and density and mass and materials balance. All right, everybody got a paper? And of course, remember, it's okay to chat amongst yourselves. This is not quiet time. Let's talk a little bit about carbon filtering. And actually, it doesn't filter. Carbon filters, that's kind of a misnomer, because when we talk about filtering, what that normally implies is straining. That's what most people understand filtering to be, is like a physical separation of a solid constituent from the liquid that it's being contained within. Whereas really the way that carbon works is through the process of absorption, which is that if you had, for example, an organic pollutant in water and that water trickles through the carbon, the organic pollutant would be attracted to the surface of the carbon. And so it would absorb to the surface of the carbon rather than, it's not that the dissolved organic constituent is somehow screened. But anyways, activated carbon removes pollutants through adsorption. So carbon, carbon molecules are attracted to other carbon molecules, and activated carbon is activated in the sense that it has a large specific surface area. It has a very porous surface with a large surface area so that the water has lots of points of contact with carbon as it's flowing through, so that the dissolved molecules in the water just want to stay stuck to the carbon that's the solid. So it's good at removing chlorine and sediments, but mostly it's effective for organic materials. And organic materials, what that means is those chemicals that have a carbon molecule in them, such as volatile organic chemicals. So things like dry cleaning fluids sometimes get into the water supply. Trichloroethylene is something that would be effective for removal through carbon filtering. When I was a student, I went on a tour of a water treatment facility where they had carbon filtering because there used to be explosives production in that part of the valley. Like they were making an explosive, I think called HMX or maybe RDX. It was some kind of an explosive that they were making, and it seeped into the water, and they used the drinking water came from groundwater there, so they had to filter all of the groundwater through carbon, similar to if you've seen like a Brita pitcher that goes into the refrigerator. That's also effective at removing organic materials. And so those explosives were organic materials that were filtered out by the carbon at that location. So it's not effective at removing minerals like manganese, calcium, iron, salts, sodium chloride. Inorganic constituents are going to pass right through a carbon filter. And when I did that search, I got the details from Wikipedia. Maybe you used ChatGPT, but it's always good to source the information that you were repeating there, just so we know what the citation is. All right, so part 2 of this is asking, so let's say that a kilogram of carbon can bind 0.15 kilograms of an organic material that's polluting groundwater. 3 carbon tanks can hold 1,800 kilograms each. So if the flow rate Q is 25 liters per second and the contaminant is in the water at a concentration of 3.4 grams per cubic meter, then how long until the carbon needs to be regenerated? And the way that they regenerate carbon is once there's saturation of the surface of those carbon molecules, they don't have to throw it away. What they can do is they can actually heat it up, and that'll cause the volatile organic compounds that are connected to the carbon to go into the air. And sometimes they burn them away, but they can reuse carbon over again by going through kind of a refurbishment and refreshing process, regeneration. All right, so what this is showing is our flow rate is 0.025 cubic meters per second. And the amount of carbon that's there, if we've got 3 of those tanks, is 5,400 kilograms. And let's just say that each kilogram of carbon can take 0.15 kilograms of pollutant. So that means that the amount of carbon that we have available, we're going to be able to remove from the water 810 kilograms of pollutant before the carbon filter is saturated. And if we don't regenerate, what that means is that now the pollutant would just pass through the carbon filter and it would stay in the water, which we don't want. So here this is a mass flow rate problem where what we're looking at is the mass flow rate of the pollutant is equal to the volumetric flow rate multiplied by the concentration of the pollutant. So the question is, how many grams per second of this pollutant is being removed, and what's our limit? If our limit is, with the available carbon, we can remove 810 kilograms, that's how much capacity we have at the beginning, and we're removing it at a rate of 0.085 grams per second, then that works out to what I did. Instead of calculating the concentration in kilograms, I just said, well, 810 kilograms is 810,000 grams, and we're using up 0.085 grams of capacity per second. So you can see the number of seconds, and then I divided that number of seconds by 86,400 to get the number of days. So it's going to be 110.3 days before the carbon is depleted and needs to be regenerated. So that's just an illustration of how we can use the mass balance. If we were going to draw a little sketch of what's happening in this system, we've got the tanks, 3 of them, and I don't know if maybe it's coming in and going like in series, like this is showing. This is series, one after the other, or maybe if it was parallel would look like if the inflow pipe was connected to the top of each one of them. So parallel would be it's going in, it's going in, it's going in, and then it's coming out. It doesn't actually matter if it's series or parallel in this illustration. We're going to get the same answer. But what we do is we draw a control surface around the volume of interest, and we look at the pollutant coming in, and what we want is no pollutant going out. We want 0 grams per second going out. So there's a certain amount of pollution coming in at a certain rate, and it's staying inside of the control volume. That's the purpose of those carbon filters, is to cause an accumulation of the pollutant inside of the control volume. So this is just an application of mass balance. Does anybody have any questions on this problem before we move on? Yes?
So when you give us the flow rate of the system, so that's the flow rate for the whole system, not like each tank?
Good. Yes, that's true. That is the overall water that's coming in. And so yeah, we didn't have any information about if the tanks are connected. So yeah, if I did want you to split it off, I would have said water flow rate of 25 liters per second for each stream. So like if there were 3 separate streams going into the 3 separate tanks, that's how I'd phrase that one. It's good that you're thinking about that. Are there other questions? All right. So just a review. When we talked about mass balance on Wednesday, we assumed that the flow was steady, meaning that the conditions are constant over time, that the flow rate's not speeding up, it's not slowing down, it's steady. And we also talked about how accumulation is just in minus out, and for now we're either only focusing on systems where there's no reaction or we're neglecting the reaction. That's the simplest case of mass balance, is accumulation is in minus out. So in a reactor like this, we'd have flow in, flow out, and depending on the difference between the two, the storage maybe is going up, like the tank is filling, if in is greater than out. Or if out is greater than in, then the water level in the tank would be decreasing. And I don't know why we're stirring the tank, because there's no reaction in this first illustration. But that's obviously not always true. You don't always have steady state conditions because, as I've mentioned before already, human behavior varies during the day. So think about the amount of water that you use in the middle of the night compared to the amount of water that you use at 8 p.m. There's variability in human behavior. There's variability in things like temperature. And there's also variability having to do with the weather patterns. And so there's changes in the flow rate coming into reactors that we can describe through daily peaking factors if we want to look at the extremes of the extreme of low flow rate, the extreme of high flow rate. The other thing is that there are reactions, and thank goodness for that, because it's those reactions that we're going to harness to clean up the water. So just as an illustration, we use aeration basins as a place where we encourage bacterial growth to break down pollutants. And one of the most important pollutants that we keep track of in environmental engineering is called biochemical oxygen demand, BOD. And we'll talk in a lot of detail about BOD, but it's a very general term that's just talking about how if you take wastewater and dump it into the river, the bacteria that naturally live in the river, they're going to break down that waste because it's an energy source for them. There are bacteria that can live on anything, and there are bacteria that break down human waste. Human waste is their food. But the other thing that they consume in addition to that human waste is they consume oxygen. And that's a real problem for us because if the bacteria that are eating our waste in the river use up all of the oxygen, then it's going to kill the fish that need the oxygen, which is dissolved in the water in the river. So, broadly speaking, we keep track of this biochemical oxygen demand because it it affects the water quality in the receiving bodies of the streams that are taking wastewater. So there are reactions that we have to keep track of, and this aeration basin is one of the big thoughts of civil engineering. Like there are some like really key ideas in civil engineering that were the groundbreakers, like putting steel reinforcing into concrete. That was a game-changing idea. In numerical calculations, there's this thing that we learn in hydraulic engineering called the Hardy-Cross method. It was a groundbreaking idea that allows us to calculate the pressure in a complicated pipe network. So another one of these big ideas that totally changed the game was, I've talked about this before, activated sludge, and putting waste that we collect at the bottom of a clarifier into an aeration basin and kind of stimulating the bacterial growth to break down BOD in the aeration basin so that it doesn't happen in the river later on. So we need to have some tools available to us to combine mass balance with reactions. So let's talk about reactions and the rate at which they occur. So by rate, what we mean is the change of something over time. And we could talk about the rate of accumulation of fluid volume. That would be cubic meters per second, let's say. If there was more water coming into a tank than going out, then the volume would be accumulating in that tank, and we'd keep track of that through a volumetric basis. But we can also talk about rates in terms of mass. So we could talk about how many kilograms of water are going into the tank over time, or we can focus on not just the water, we can focus on what is the water carrying that we're interested in. So in this example that we just worked, we were keeping track of the mass balance of the certain organic chemical. That was, the mass balance was not of the water, but it was of the chemical that we cared about. Or if we're talking about wastewater, maybe what we're going to do our mass balance is on the BOD, the biochemical oxygen demand. So the rate is just how many kilograms per second is either passing into the reactor, or if the reactor is designed to consume some chemical constituent, what's the rate that it's being broken down inside of the reactor. So here's how we transform that very simple accumulation equals in minus out. That's what I told you last time. Accumulation is equal to in minus out if there's no reaction. This is the real answer of what's happening with mass balance, because now we are going to account for chemicals and biological reactions happening in a reactor where maybe there's some production, maybe there's some consumption, and in some cases there's both production and consumption. So in an aeration basin like this, there are bacteria that are growing in this aeration basin because they're breaking down the BOD. But then there's other bacteria that are predators that are consuming the producer bacteria. So it's a complex ecosystem. Aeration basins will have a wide variety of bacteria and other microbes as well. And so we could, in a single reactor, have both some constituent flowing in, flowing out, and it could be produced and it could be consumed. So potentially all four of those things are happening on the right-hand side of the equation, where what we want to know is inside of some control volume, how is the rate of the mass changing over time? So dm dt is just saying, what's the rate of change in mass over time? So it's related to the mass flow rate in minus the mass flow rate out, and then the net difference between production and consumption. So if you're having both production and consumption, one is bigger than the other, and so you just look at the net difference between the two. And so here, R means the rate of the reaction, and then V with a line through it, that means volume. Sometimes we use the letter V in two different ways. V can mean velocity, but then if it's got this line through it, that's generally meant to indicate volume. So the rate of mass changing in a reactor is the reaction rate multiplied by the volume of the reactor. And then that would give you mass per time. So we'll apply this through several examples. But what I want to do is I want to tell you a little bit about the rate of the reaction. So any questions so far about mass balance? Reaction rates. Okay. The change of some constituent, it could be a chemical, it could be bacteria, it's just the change of something over time is equal to R. That's the reaction rate. Reaction rates can follow different pathways, or they can exhibit different types of behavior. And a zero order reaction is what happens when the reaction rate is constant and it's not affected by the quantity of the constituents which are present. So R, the reaction rate, is a constant, K. And we can quantify the constant. So what we're saying is that the change of A over time is some constant K. And so here's an illustration of what that would look like if we graph it. If we graph the reaction, then the accumulation of amount over time is linear. So at the beginning of the reaction, when we don't have very much of the constituents, the rate of the reaction is the same at the end. So it's not slowing down, it's not speeding up, it's just plugging along at the same rate. We call that a zero order reaction. And when I was working on my PhD at Purdue, I was characterizing the kinetics of inorganic sleeve fouling in UV reactors. UV reactors are used to disinfect drinking water. It's a way to kill bacteria in water, is to shine really bright UV lights, and it makes it so they can't reproduce. And if bacteria can't reproduce, then they can't make you sick. So it's something that I was studying. Mainly I was looking at how when you put it in water, sometimes the quartz sleeves that the lamps are in, they'll get fouled with inorganic material. And so I studied that for 3 years, and we came to the conclusion that the fouling rates of reactions were zero order in inorganic sleeve fouling. So it's the least interesting kind of reaction because the rate is constant. But, you know, they do exist, zero order reactions. So what it means, the reaction rate is independent of the amount. Whether there's a little or a lot, the reaction rate is just constant over time. First order reactions are different because the rate of the reaction is proportional to the amount that's present. So just as an example, bacteria consume a substrate, by which I mean food. So bacteria, they break down what is our waste. They'll use any organic material. You could throw like sugar into the river and the bacteria would consume that sugar. It's an energy source for them. So bacteria consume their food more quickly when there's lots of food. And when there's less food, the rate of consumption decreases. So I think we all kind of understand that instinctively, that sometimes the rate of the reaction depends on how much of something there is. And that describes first order kinetics. The reaction rate is the amount times some rate constant. So the units of the rate constant, K, are inverse time. We'll talk about that, but just the units would be like hours to the -1, or they would be seconds to the -1. The formulas that we're going to put rate constants in dictate that the units have to be inverse time. If we were going to graph a consumption reaction, this would be an illustration of a first order consumption reaction where the amount is going down, and at first the slope of that line is pretty steep, which means you're losing a lot per unit time. Whatever's happening here, whether it's a chemical or a biological reaction, the rate that this constituent is being consumed is fast at first, but then it's slowing down. And how can we tell that the rate of the reaction is slowing down? Because with each unit of time, less and less is being lost. So the curve is flattening out. And I think you can see that. And the change in the amount is getting smaller as the reaction goes on. So this is a consumption reaction, which is first order. Here's a production reaction, which is first order. And what you'll see is that the rate of the reaction in this case is increasing as the amount goes up. So think about if you were producing in an aeration basin, if you're trying to breed bacteria. At first, when you don't have very many bacteria, then the replication isn't as fast as when you have a lot of bacteria. So the more you have, the faster things go in a first order production reaction. So how can you observe first order? Well, you kind of just eyeball it a little bit, or you can identify it. If you've got a data set like this and you graph it, that's not linear, obviously, but if you do the logarithm of the amount and you graph that, first order kinetics will give you a linear trend when you take the logarithm of the amount on the vertical axis and time on the horizontal axis. And then the slope of that line is the rate constant, K. So this is a sneak peek of what we're going to be doing with kinetics, is we're going to be using K values in order to predict how amounts change over time. Any questions about this? I wish this class was 75 minutes. There's just not enough time to talk about all this good stuff. And I don't think we're going to get to the illustration that's on the front side of the paper. But I'll show it to you quickly so you'll at least get the idea of what I was going to have you do. So second order kinetics really depends on the amount that's present. It's even more sensitive in second order reactions to the quantity of whatever's there. So remember, first order, the rate of the reaction is influenced by the amount that's present. In second order kinetics, it's influenced by the amount present squared. So the rate constant is the K value, which is the coefficient that describes the rate of the reaction, the rate constant multiplied by the amount squared. So the change in the amount over time is equal to K times A squared. So you get really wild swings in the amount, the rate of production or consumption based on if A is going up or down. So this just shows, for example, you started out with a certain amount and it's declining more rapidly as the reaction goes on because it's more sensitive. So it's not linear if you do that trick that we showed before of the first order kinetics. The first order kinetics gave us a line where we had the logarithm on the amount of the vertical and time horizontal. It's not linear. Well, it's because this isn't a first order reaction. This is a second order reaction. And the way that we would observe linear behavior for a second order reaction is if we do, for the vertical axis, 1 divided by the amount. So if you do 1 divided amount here, and then time on the horizontal, now that'll give you linear behavior, and that is how you can identify whether it's a second order reaction or a first order reaction. Usually you can tell just by inspection, just by looking, you can tell if it's zero order. But then if the data is nonlinear, then you have to be a little bit more cautious about diagnosing whether it's first order or second order. And so the key is just take the data and logarithm graph it, take the data and inverse graph it, and then depending on which one gave you linear results is how you're going to know whether it's first or second order reaction. The other thing to note is that for a second order reaction, you would have a positive slope for a consumption reaction. So you'd have a positive slope when the amount is going down. Any questions about second or first order kinetics? We're just laying the groundwork here for design, analysis. This is the theory. This is the fundamentals, the science that we have to know in order to do the engineering, which is problem solving. This class is a mix of both. We're learning some science so that we can use the science as a tool to solve problems in engineering. So this is what I was going to have us do for this example. Got 3 compounds. we want to know for each of them whether it's first order, zero order, or second order. And then also we want to know what is the rate constant for each of them. So let me take you through that process. I'll demonstrate this. By inspection, can you tell which one is the zero order compound? Which compound is exhibiting zero order kinetics?
Compound B.
B. Compound B is zero order. And how do we know that?
It's decreasing linearly.
Exactly right. It's decreasing linearly. Every hour, it's losing 3 milligrams per liter. So by inspection, compound B is zero order kinetics. Now, what about these other ones? Compound A, compound C? I don't want to guess. I want to graph it and find out for sure. So here's what we do. I'm just going to copy this and paste it into Excel. Oh, I can't because this is an unlicensed product. Hopefully Excel is licensed. Okay, no problems there. So what I'm going to do is I'm going to recreate that table. Time in hours, compound A, and then we're going to skip over compound B because you correctly deduced that is zero order kinetics. Compound C. And you've got the handout there so you can see that what we're going to do is go through hour 5, and we're going to just through graphing diagnose what is the rate order of both of these. And well, I don't know what's happening over here. Maybe you already have your guess on which is which. It is a little bit obvious to begin. I'm not sure what's happening. Oh, unlicensed product. See all these over here? Did it decide it didn't want me to do this? Why is it so? And this is not a view I'm familiar with. Anybody know what we're looking at here? Oh, normal. Okay, still pretty weird. I mean, I think of myself as pretty good with Excel, but those are things I've not seen. Let me just open up the key. Let's see, rather than creating it from scratch, maybe we've got enough time to look at the solution. Here's what I did. This is compound A doing 1 over A. And so when if I do the logarithm, okay, so this is just compound A graphed outright. It's not linear. If I take compound A and I do 1 divided by the concentration, then it's linear with an R squared of 1. In reality, you'll never see an R squared that tight. It's because I synthesized this data. But so it's second order kinetics. Compound A is second order kinetics because when I graphed time on the horizontal axis and 1 divided by the concentration on the vertical axis, then it became linear. And so then the other part of the question is, what is the rate constant? Like, what's the K value? So the K value here is 0.04. So 0.04 is actually what I used as the K value to get this, like these numbers. I generated these numbers by starting with the K value that I knew and then substituting into the formulas that we're going to use starting next week. So you don't know that formula yet, but you'll know it soon. But the main point of this example was just to diagnose what is the rate order. And it's second order for compound A. And then how do we know compound C is first order? It's because when I took the logarithm of compound C and then graphed that on the vertical axis, time on the horizontal axis, then I got linear behavior. And so the constant, it's the slope of the line, 0.31. So it was a first order reaction with K equals 0.31. So I think your homework assignment has you doing something like this, dealing with kinetics. So, you could get started on that next assignment that's due a week from today. Let's just, before we go our separate ways, revisit the announcements. All right, so you've got the book. You're going to read the book. Maybe you're going to go to the presentation next door. Homework 2 due on Friday, a week from today, and then quiz 1 the Monday after that. All right, that's all I've got for you. I guess I'll let you go early, 2 minutes early, start your weekend. All right, see you on Wednesday. We don't have classes on Monday, so I'll see you Wednesday.